on to the final session of this afternoon, and we're very happy to start with Pierre Vanhove, who's going to tell us about classical observers from the exponential representation of the gravitational S-matrix.
Thank you very much. So thank you very much for giving me the opportunity to talk about a very exciting subject. I mean, sorry for the long title, but so the topic of the... It's on? No? It's not? Let me check. Okay. So maybe it was misplaced. Oh, I see. Oh, it's okay. I've got it. Okay, so the topic is about, applying all the modern ideas from quantum field theory to compute actually observables in classical gravitational S-matrix, and in particular with the application to the physics of gravitational waves. So, in fact, this is a very exciting subject that has been blooming in the recent years. So, I'm not going to give you a review talk, and many people have contributed to this subject, in particular Carlo Heisenberg or Rodolfo Russo that are in the room. And the upshot is that actually there has been huge progress in the understanding of the analytic structure of the in-spiral phase between two-body interaction, interacting gravitationally, with spin or without spin, and using, to a large extent, the approximation of the black hole as point particle. So in fact, when you look at the dynamics in the in-spiral phase, there are, so the parameters are the relative velocity between your two massive objects. And so you can do a small velocity expansion combined with a small weak coupling expansion. Okay, so this is the post-Newtonian expansion that was actually started a long time ago by Einstein. And then what you can think of is that when you use the amplitude setup, we will be actually doing a fully relativistic computation. So that means it will be valid for all values of velocities from the static case to ultra-relativistic regime. But this is a weak coupling expansion order by order in G Newton. And there is another approach that is used as well by the GR community, is to do what is called the self-force expansion, and I will explain that in the last part of my talk, which is a case where you have one big mass and one small mass, and you do an expansion with respect to the mass ratio, but this is with some to all order in G's. So when you are in a post-Minkowskian, the two masses can be of same size, and then here this is more like when you have one perturbation of a small mass near a big mass. So, in fact, I said the subject is not new, so there have been already a lot of results that have been accumulated, and to show you how good we are getting by doing this perturbative computation, I'm coming in a minute to tell you what kind of setup we use. This is a graph that is selected from a paper by Thibaut Damour and Pierre Vanhove, which compares the PM here means an expansion with respect to G Newton. So 1 PM is 3 level, 2 PM 1 loop, 2 loop, 3 loop, and 3 loop has been completed. And they compare it to numerical GR, and then you see that when you include what they call radiation, and I will mention that what I mean by radiation, you have very, very nice match between the analytic result and what you get from numerical GR. So this is telling you that even for a problem like that, that is of very, very, huge physical importance, because we get a lot of data from the ground-based interferometer. We are preparing as well data for LISA. That all the technique developed from what we learned, quantum field theory technique, are really, really, they show their value applied to this physical problem. So the fact that I want to tell you, if you, I'm not expecting that everybody is familiar with the subject, is that if you do, so here is the post-Minkowskian approximation, which is a perturbation. So you have your two-body system, you do a perturbation, a weak coupling expansion, and you are valid in a regime that overlaps with the post-Newtonian expansion, correction to small velocities, up to the ultra-relativistic regime. Okay? And the fact that you can interpolate between the static case to the ultra-relativistic regime in the post-Minkowskian approximation is an important fact, because when you talk about this gravitational system and the way they interact, there is the question of gravitational radiation. And this radiation is an important piece of the computation. If you don't control that, you don't have an understanding of the physics of your system. Okay, so concretely what you do is that you have your two objects, either a pulsar or two black holes or whatever, but you approximate as point particle, mass m1, mass m2. You have an Hamiltonian that depends, gamma is the relativistic factor, so that's V is the relative velocities. And here you have a potential that you want to expand in powers of g Newton. So at the leading order, you get the relativistic version of Newton's potential. When the two objects are not moving, you get that gamma is 1, and you get the usual standard Newton's potential that you have learned from textbook. So the thing is that what is important is that this potential, so the thing that you want to put here, this Hamiltonian is the thing that is going to be used by people who want to analyze the waveforms. So this object has a sum over the g Newton, okay, so the masses and the relative distance, so this is essentially dimension analysis, and something that depends on the mass. But you see, there's an very extremely important property that at each order in perturbation, the mass dependence is polynomial. And that's a very non-trivial fact, but it's an important fact. And in fact, the question is that how do you build an object that is such, a scattering amplitude that is such that when you Fourier transform from direct space to momentum transfer, you get exactly what you need to put in this Hamiltonian, okay? So if I do the Fourier transform back from 3 dimensions, I'm going to need momentum transfer to this power that depends on the loop order, and this, R is there is no R, so Q is just a spectator, okay? So the question is indeed, is it possible that you solve a classical problem? It's purely classical, but gravity interacts with itself, so it's a nonlinear problem, by using a scattering amplitude with an appropriate classical limit, h bar to 0, so that you have a fully quantum object, quantum gravity, quantized gravity, so that then at the end you get a classical object that exactly you want to put in this Hamiltonian and give to the people who do data analysis for gravitational waves. So this was suggested already, an approach that was suggested by Kovacs and Thorne quite some time ago, in 78, and this is exactly what we're going to explain. So within the framework of a point particle approximation, you do the following. So you take your Einstein-Hilbert action, okay, this is Newton's constant. So here I'm writing 4 dimensions, but at some point I'm going to compute amplitude that will have UV divergences, but they are not of interest for us. But even the classical part, you have to control the infrared divergences from the radiation. So you will have to be working in a framework of dim reg. So in fact, I will be working in 4 minus 2 epsilon, okay? Then here I'm looking at two massive objects that I'm taking here two scalar fields, for example, two Schwarzschild black holes that are represented by these massive lines. And so this is quantized field, this is a quantized field, and this is the graviton propagation, this is a quantized field, okay? So you have the problem of computing an amplitude for two heavy masses that are interacting gravitationally. So, and the energy that is going to be exchanged between the two is weak, okay? It's small energy transfer. But you do standard perturbation around flat space. So, of course, if you want to have Kerr black holes involved, I mean, you will have to include the spin, and people, I mean, know that, except the problem is that when you have spin, the algebra is getting more messy, so I'm going to confine myself to the Schwarzschild case, which is the scalar particle. And so you have your total S matrix that is the sum of all the perturbative contribution. So look what you get at tree level. So you have the 2, so this is mass M1, mass M2, that they change one graviton exchange. So it's an easy process that everybody in the room can write, but let me put the H bar maybe in a way that is maybe non-natural. So the fact is that here you have Q, the momentum transfer. So what I define is that I call Q to be H bar, the wave number, so underlying Q. Then I have H bar that are this way. There's a piece in purple, no H bar, there's a H bar piece, and here there are H bar. So if I can expand, I see that there is a piece that is 1 over H bar, something that depends only on the velocity, Q square, and a piece that depends on the H bar. If I Fourier transform that expression, I mean, in 3 dimensions, I'm getting exactly Newton's potential. So in fact, you see that the classical result, that is relativistic Newton's potential, comes at the 1 over H bar piece of a tree level, 1 graviton exchange. And there's an H bar piece, which is, as you know, this is the contact interaction that tells you that at very high energy, you have potential UV issues, right? Let's look at what happens. Suppose you have here, so I'm taking a process like that. I suppose I have loops here, and then I'm isolating one graph that touches one of the massive particles. So let's call it either M1 or M2, where I have a triangle. So here, this is my triangle, and then if I look at this, and this is the graviton. So this local one-loop triangle graph has these two propagators, and here is the propagator for the scalar particle. But if you remember that in the Klein-Gordon equation, it's the quantum wavelength that comes in, there's H bar here. So if you do a small H bar expansion or a large mass expansion, which is in fact very similar because you have a small energy transfer, then the finite piece of that triangle contains a piece that is MC over square root of Q square, 1 over H bar, and a piece that is a log Q square over mu square, which is the infrared part. And this piece will exactly be the one loop correction, which is 2 pm correction to the classical potential. This is what I will put as the G cube order in my classical Hamiltonian. And then I have a piece that has to do with some quantum corrections. Okay? So that is what you see at the level of simple computation. And this thing was noticed already by Iwasaki a long time ago in the 70s, but at some point, kind of the amplitude technique, quantum field theory, was not developed enough for making it systematic. So, but the logic was there. I I don't want to claim originality. The fact that you have classical pieces at every loop order was actually noticed as well in other contexts in a nice paper by Barry Holstein and John Donahue. Okay. So, in fact, if you have a large mass expansion, and this is where actually the fact that the potential we are looking at in the Hamiltonian is polynomial in the mass is kind of important, that there is a statement that at any loop order in perturbation, if you take this limit where you work with the wave number, then you have an expansion of your gravitational exchange between your two massive particles that has this form. 1 over H bar to the L plus 1, blah, 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 plus 1 over H bar, so this is the Laurent expansion, plus pieces that is order 0 in H bar, constant, or higher orders. So it's different because you are used to the fact that every loop order scales like H bar to the L minus 1, so they are suppressed. It's not the case. And in fact, if you just blindly first forget about that piece and you just took that piece that you have computed, extract this coefficient, then you Fourier transform it to direct space, then you get an expression that is exactly what you want to put in there. And in fact, if you have computed something here, if you do a small velocity expansion, you can compute with what people from the post-Newtonian approximation, and then you see there's a perfect match. So in a sense, I mean, there have been a lot of checks about the fact that this residue of the 1 over h bar pieces that you extract this way is exactly giving you what you need to put into your two-body effective, Hamiltonian, that it's capturing the right physics. And the thing is that what I said is that it's valid for gamma from 1 to infinity. So in particular, if you have a knowledge about what happens at ultra-relativistic regime, and this is where Gabriele Veneziano comes very useful, is that you can actually check that your amplitude extrapolates very well to the high energy regime. So the thing is that, now why do you have this 1 over this Laurent expansion? In fact, it's not very surprising. So what you do is that you have your S matrix. Usually you write it at 1 plus the T matrix. In fact, if you just exponentiate it, such that you have an operator n that is, that has a piece that is both integer powers in G Newton and a piece that has half integer powers in G Newton. So this is the piece that allows you to emit graviton on the axonal legs, that are radiations. Then what's happening is that the presence of these guys are exactly what you need in order to be able to re-exponentiate your S matrix element and keep, in fact, in the exponential, just the piece that you call the classical piece. So the exponentiation, which is kind of iconalization, but iconalization in a very smart way, tells you that you need actually this bizarre-looking limit of the any loop order. So one of the examples is, one of the things you can do is that actually you can, Kosover maybe and O'Connell, they have explained to you that indeed the right way to define your classical observable, the one you would give to your GR colleague, is through a prescription. When you take the matrix element, you do the Fourier transform, and then you have this delta function localization. And this is the KMOC, which tells you that actually you are computing the difference between the out-out and the in-in states. So if you massage this expression, you can rewrite this in terms of an infinite series of nested commutators, where these commutators are this n operator, where you have here the operator you want to compute that. And then if you do that, then you show that precisely because of the structure of this term and the exponentiation I just described, which is actually linked as well to unitarity of the theory, then the limit h bar to 0 is totally fine. So there is no issue. So in fact, depending on the way you organize the computation, and actually these people in their paper, they had shown by a careful computation that all the singular piece would cancel, leaving you a finite result. But so the thing is that what they were missing is this formalism that streamlines the approach. Then the h bar going to 0 limit of this operator is just the classical piece plus potentially quantum corrections. Okay? So in fact, it's an interesting fact because you have a full control from a scattering amplitude point of view. So you apply unitarity, everything you like, integral reductions, your favorite program from QCD, whatever, and you can compute this PM expansion. If you are a fan of modified Einstein theory and effective field theory that modifies Einstein gravity, then you can as well extract quantum correction to your classical observable. Okay? So this is a very, very generic setup. It works, it has been tested, as I said, there's a huge literature on that, and it works wonderfully. So what's happening is that for the one that are familiar with the thing that is the word line formalism, when you have classical sources that interact gravitationally, okay? So the relation between a quantum field theory, for example, when you have quantized field, my massive field quantized that are change massless gravitons, like that, is that when you apply these relations, you have at some point to use the completeness relation. And the completeness relation has, in the phase space integral, the delta, this is the time order, I mean the delta plus delta function. That means that project on the physical state, yeah? That is, this guy is on mass shell, and of course it has positive energy. And the fact, and this is the graviton part, okay? And the fact that you have this insertion, automatically, in your computation, when you extract that piece, you exactly have as many delta function as you have loops, and that cuts open the massive line and project exactly on the classical world line. So you can show that this formalism of scattering amplitude, quantum scattering amplitude, when you extract this classical limit, is totally equivalent to a one-line formalism that is used, for example, by Porto and collaborators, or Jan Plewka and collaborators, and I'm forgetting somebody, I think. But anyway, so this is great. So what do you get at the end? So I just summarize. So you have the exponential representation of the S matrix, and yeah, I define N as the valve of the N operator, and a bit of notation, Fourier transforming into the J. I prefer to use the angular momentum. It's standard in the literature compared to the position space, and this is the momentum at infinity. So at tree level, you get this, which is in fact the same as getting the classical Newton scattering. So from that, by differentiating this guy respect to J, you can get the standard deviation angle that you can compute from classical textbook. So this is the one loop result, okay, which is, so this is, that was known already for some time. It's a nice expression, and you see all these expressions are exactly like the contribution as if you have a test mass in a Schwarzschild black hole, okay? But then if you go to 2 loop, which is 3 p.m., you start seeing that actually the computation deviates from having a test particle in a Schwarzschild background. Okay, so the functions that appear there are a little more complicated. You have this Arcosh, so this is the relativistic invariant factors. And the important part is this red piece, which is the radiation. Radiation was essential at this order to get the ultra-relativistic regime and match what you can get from, for example, arguments like from the ACV ultra-relativistic regime. And these things, everything fits beautifully, and thanks to actually, so there are many people who contributed to that, but Gabriele input for that was extremely essential to get a coherent picture of everything. So, for example, if you compute an observable that is the momentum kick, you get an expression in the conservative sector. So conservative means I'm not allowing gravitons on the external leg. I mean, we have done the computation as well, but for what I want to say, it's not needed. So you get an expression that is there. So R is the relative position, L is the angular momentum, and then what happens is that you get an expression that involves the derivative of this N operator with respect to the angular momentum. If you go to a classic textbook, Landau-Lifshitz or Thibaut d'Amour, then you see that the expression that you get here is exactly what you expect if N is what is called the radial action. So the fact that is the object that is conjugated to the conserved energy momentum in your system. That means the scattering angle that you can compute, which is the differentiation of N respect to J, that should appear here, that has as well a perturbative expansion in terms of the Newton's constant, is actually computed by this formalism and resummed for the conservative sector in a very nice formula. And this is one nice thing, is that you see that this N operator that I say looks like the iconal operator is really the equivalent at a quantum level, because a priori you have a quantum operator that can contain much more. But in the sector where you don't have radiation in just the conservative sector, the valve of this N operator is really what you want to be as the classical radial action from classical mechanics. Okay, so In fact, I mean, you can apply that to higher orders, and there are people doing the computation at 5 p.m., and the logic is the same. I mean, the formalism works, except that it's much more involved, and in fact, computation is not yet finished, so I cannot. This is why I'm going to switch gear a little bit. So in the last few minutes, so I'm going now to tell about a different regime, which is the last point of when I started, in the list I gave at the beginning, is that when I have a big black hole and a small black hole, a small perturbation. In that case, what you want is that you want to understand the trajectory of that small object, little m, in the exact background of this massive black hole. So in fact, what you want to do is that compared to what I had before, I should have put that formula, where is it? Instead of, organizing the sum over Gn and then summing over the mass, you just exchange the two summations, okay? It's a reorganization of the same quantity. So you organize it by powers of news. News is little m over big M, and then you have here something that is a priori to infinite order in G Newton. So what we have found realized with Stavros is that if you couple, if you use the cubic formulation of Einstein gravity that was introduced by Kirchhoff and Rennen some time ago, which is not doing perturbation with respect to flat space. So usually we all do, and I was doing that for a long time, eta mu nu plus kappa h mu nu, with indices downstairs. If you do it with what is called the Gothic inverse metric, and you do perturbation this way, you can find a gauge where your Einstein interaction is purely cubic. So this is your degrees of freedom for the metric, and then you have an auxiliary field. And what happens is that only the G couples to your matter field, okay, so the two word lines, the mass 1, mass 2, and the auxiliary field doesn't couple directly to them. So what's happening is that if you then write the effective action for your two-body system, using a word line approach, I explained that it's equivalent to the other approach. By integrating over degrees of freedom h of the metric and the auxiliary field of blah, 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 then you get an effective action that is the word line action of your AV object, and then the effective action for the word line action of the light object expanded in powers of little mass over big mass. And here you have the trajectories, and at the leading order, for example, you can consider that this is static. Okay? So why is this useful? So it's useful because if you look at the graviton emission in that formalism, here is the form factor for the graviton emission, the waveform, and here for the auxiliary field. Then, because it's purely cubic, it has at loop order n, it's just the sum of objects of loop order n minus lower loop order. It's like the Behrens-Gill type of reduction. So, because it's cubic, there is a recursion relation. We have been able to derive to all order in G, perturbation. So what you do is that you parameterize the form factor with, and then you get exactly a recursion relation that is quadratic, that you can solve in 4 dimensions and it gives you a Schwarzschild. Exactly. You can solve it in 5 dimensions, you can solve it in 6 dimensions. Every dimension, because all this quantum field theory I've been telling you is valid in any dimension. So, in fact, this is the first time I know that you have been able to derive an exact metric from a scattering amplitude point of view. And it's based on this cubic formalism. Now, if you want to do the next order, which is the zero cell force, which is the geodesic. So this is the geodesic, the small mass that interacts with the big mass. So here there is one graviton exchange, but this one has an infinite resummation of the loop order because you have created the black hole metric. Yeah, so this is infinite sum, and then you couple twice, etc. So you can do it as well. And what we have done is that we have been able to resum as well and get the geodesic. It's exactly like that. No effort. So the one cell force is on the way. So in fact, so this is why I'm concluding, is that we are at a stage where we have an efficient tool. So of course, in this in-spiral phase, there will be a point, 6 p.m., where this perturbation is going to break down. So you don't expect to be able to go to the merger. But still, to very high order in perturbation, you can provide an analytic formula, you can understand gravitational radiation, you can understand a lot of things using the setup of quantum field theory as you are familiar with, although you are just looking at a classical GR problem. The other point, which is very nice, is that actually this h bar going to zero limit, this way the classical physics emerges from quantum physics, is just in fact Bohr's correspondence principle. You have a large mass. It's when if you do large, heavy quark expansion in QCD is the same. It's the same. But this is a large mass expansion, so it had to work. You had to get the classical physics out of the quantum scattering amplitude. So, and for the cubic formalism technique, which is nice, is that actually it gives you an end to do really all order with summation. It's surprising that you can use quantum field theory to resume to all order in perturbation. There is no non-perturbative effect here, but and so this is where you can then study, say, the cell force, the love number, the vanishing of the love number for the Schwarzschild black holes, for example, like that, which are important questions regarding the fact that maybe we are detecting very small mass black holes. So this is what I wanted to present today. Thank you.
Questions?
Yeah, I have a couple of quick questions. One is, how did you deal with the UV infinities of the loops?
Oh, that's a good question. They are there, but they are not contributing to the classical result. So, yeah, I've been a bit fast on that, but this is UV. So, okay. So at one loop, it's easy. In fact, for example, the UV divergences are log in 4 dimensions, and the classical are square root. So even by unitarity, you can just compute the square root cut. So when you go to higher loops, of course, then you have to make sure you separate them. But they are there. And in fact, it's interesting because, okay, so we have computed with John and Emil and Ludovic the scattering angle, okay, so the light bending. So we have completed one loop correction. And you can include the quantum correction to that. And people, for example, if you have your EFT and you want to bond the possible correction to Einstein's gravity to that, and you get the quantum correction to the scattering angle, and then you look the constraint on causality, Shapiro time delay, and everything is there. And then you can get constraints on your EFTs.
And for the last part with the self force, can you do high orders in the self force, or is this, in a sense, you start? Can you do, in a sense, new things that the self force community cannot do?
Okay, so the thing is that from a scattering amplitude point of view, so people have been doing these days an organization of the PM self force, so to organize this series in a different way. So at a given order in G Newton, compute each term in powers of nu, right? Because at some point, at for loop, it's getting like very, very complicated. And Zwibern and collaborator, they have nice papers about that and first result, and Plevka as well as some very, very nice result. Here, the thing that I'm thinking about is not doing that. It's really to resum. So we are getting something like a recursion relation on the coefficient. The problem is that, yeah, getting an analytic formula is not expected, but at least you can do something with it, which is going to all orders, but at a given powers of nu. So already one self force at all order, would be a fantastic result.
So, you mentioned at some point the perturbation will break. Yes?
Yes.
Why it will break?
Oh, because Well, there are many reasons for that. So the thing is that here, for the merger, it's a strong, so perturbation is not valid. But as well, I said, I've been using a point particle approximation. So at some point, you will feel the tidal deformation, so you need to go beyond the point particle approximation. So you can use, effective higher order operator on your word line formalisms to treat that, and it goes beyond the point particle approximation.
And here you're obtaining, with this perturbation, the Schwarzschild metric, right?
Yes.
Could you obtain other black hole-like metrics, and what would you need to change?
Okay, so for Kerr black hole, computation has been done. Essentially, the same PM story with spin has been done, but to lowest loop order. And the reason is essentially because it's much complicated, technically to compute, right? So I don't see any reason why.
It might be a bit of a tangent, but I was wondering, is there a way to read off higher order corrections to things that appear in log numbers, to see that why the log numbers of black holes are 0? Is there any relation to amplitude that?
Wait a few months. No, weeks. I don't know. Wait, you will get the answer soon.
Okay, so it's.
Thank you.